Welcome to the lecture on partial redundancy elimination. In the last lecture, we looked at an example of what exactly is PRE. Just to recapitulate a bit. So, here is an expression A plus B and here is the same expression A plus B again, and the question is can we use the computation of A plus B in this basic block 1 and avoid recomputation of A plus B in basic block 4. Under certain circumstances it is possible. So, please observe that the expression A plus B is not completely available at this point. It is available partially along this path, but it is not available along this path. So, that is why this is a partial redundancy, it is not a full redundancy. If it is full redundancy, we can simply apply global common sub expression elimination, but since it is partial redundancy, we have to insert a computation h equal to A plus B in along this arc by breaking it. Now, the expression A plus B is fully redundant at this point, it is available along this path and also this path, and we can replace this A plus B here by h, where h is the variable you know storing the value of A plus B along these two paths. So, now we were looking at properties of expressions at a point. So, availability is a well known property. So, we already have learnt about it. So, it says computed along all paths reaching P from the start node with no changes to operands. Partial availability says computed along at least one path. So, that is the difference, not all paths, only at least one path. Anticipability, we have studied this as well under very busy expressions, computed along all paths starting from P to the end node. So, that is it is useful later on with no changes to operands, and partial anticipability would be computed along at least one path from P to the end of the flow graph. So, here is an example of both. So, in A and B in these two figures, A plus B is partially available at entry to 4. So, here it is partially available because from here you can use this path and it becomes partially available, and for this point 4 we can use this path and it is partially available. It is not fully available in either of them. In A plus B is partially anticipable at exit of 1. So, exit of 1 is here. So, if we take this path it is computed, and if we take this path it is not computed. So, that is why it is partially anticipable. And in figure B, A plus B is anticipable at exit of 1 again. So, it is fully anticipable because from here it does not matter, there is only one path to take, and on that path A plus B is computed. There are more expression properties. One is safety, this is very important for us. It is defined as either available or anticipable at P, and safe partial availability is you take the path of availability and from the last computation of the expression to P, all the points must be safe. Remember, for safe partial availability you do not have to look at the path from the start node to P and make sure that all these are safe. No, that is not the point. Point is from the last computation of the expression to the point P. Okay. And safe partial anticipability is similar. All points on the path of anticipability from P to the first computation of the expression are safe. And what is a safe partially redundant computation? It must be locally anticipable, that is computed within the basic block, and safe partially available at the entry to the node. So, let us look at some examples. So, A plus B is safe partially anticipable at entry to 3. So, the dark spots are all safe points. Okay. So, let us see why they are safe. So, safety is either availability or anticipability. So, at this point it is safe because it is available, it is computed here and it becomes immediately available at this point. So, we do not have to worry about anticipability. Of course, it is not anticipable, it is only partially anticipable. The same is true here, A plus B is computed here and it is available right here. At this point it is available along these two paths. So, it is available. At this point same thing, it is available along both the paths, and at this point it is available along both the paths, and of course, it is anticipable also. At this point again it is available along all the paths. So, even though anticipability is not true in many cases, the availability makes these points safe. But remember this point is not really considered. We do not have to worry too much about this particular point. Okay. So, if even this will be safe simply because even though availability is false, the anticipability is true along both these paths it is being computed. So, this point will also be really safe. So, now in figure B, A plus B is safe partially available at entry to 4. So, all these points are safe. Okay. So, now A plus B is partially available because of this point. So, from this is the first computation of the expression along this path of safety, and it is all these points are safe from here this and this, and therefore, it is safe partially available at entry to 4. Here is an example to show what is not safe partially available. So, A plus B is not safe partially available at entry to 4. So, take this example, the computation here from the previous example is missing. So, here this point is safe because of availability, but this point is not safe because neither available nor anticipable, only partial availability and anticipability is true at this point. So, and this point is obviously therefore similarly unsafe, but this is safe because anticipability is true. Right here the expression is being computed, but we want all the points from this first computation to this point, all these 4 points to be safe, they are not. Therefore, this expression is not safe partially available at entry to 4. And in the same figure, it is not safe partially anticipable at exit of 1. So, exit of 1, the and then the computation is here. So, this all these points should have been safe, they are not, and therefore, it is not safe partially anticipable either. And in figure B, A plus B is safe partially redundant in 4. So, this computation is safe partially redundant. So, it is locally anticipable. So, it is computed locally and safe partially available along this path. So, it is safe partially redundant. There are some special computations in a basic block that we need to take note. One of them is the first computation and the other one is the last computation. The first computation, as the name indicates, is the computation before the first modification of operands from the top. So, we have not modified the operands, they take values which were given to them before, and then you evaluate the expression. So, the last computation in the basic block I is last computation after which no modification of operands takes place. So, you do not modify them, the same value is going to be available after the basic block at the output of the basic block. So, all the local redundancies are assumed to have been eliminated already. So, we will see this very soon. Hence, there exists at most one first and one last computation for a basic block. All other computations of the same expression are in between these two computations and are irrelevant. So, here is a pictorial explanation of what I just now told you. X equal to A plus B is here, then there are no modifications to A and B, then you have Y equal to A plus B. Such a situation cannot arise simply because now this A plus B is a common sub expression, we can use X here. So, we are assuming that local CSC has been carried out. So, this situation will never arise, we would have had actually Y equal to X here. Take the other situation, you have X equal to A plus B, then you have modified A and B, then you have Z equal to A plus B, another computation of A plus B, again you have modified A and B. then you have y equal to a plus b, third computation of a plus b. So, what is relevant to us is just x equal to a plus b and y equal to a plus b. The reason is before this a plus b operands are not modified, and after this a plus b operands are not modified. So, this expression is anticipable here and this expression is available at this point, and in between if there is a computation we need to do it. We will have to evaluate a plus b as many times as necessary because the operands have been modified. So, that is why these are not relevant to us, only the first and the last computations are relevant to us. So, here is our algorithm in an informal manner. So, it identifies all the safe partially redundant computations and makes them totally redundant by suitable insertions. So, what are these suitable insertions? We saw an example before. So, the x equal to a plus b was replaced by h equal to a plus b and x equal to h, and along an arc we broke the arc and introduced a computation. So, first step is we need to compute several predicates. We will see these. AVI is availability, ANT I is anticipability, safe I is safety, SPAVI is safe partial availability, SPANTI is safe partial anticipability at the entry and exit points of all nodes. So, the difference here from the previous data flow analysis is we have actually one expression and a bit vector of basic blocks for that expression. So, at the entry and exit points of the basic block we are going to compute these properties. So, one bit for each basic block and one vector for each expression. Mark all points which have both SPAV and SPANT true. So, safe partially available and safe partially anticipable points are all marked, and consider the paths formed by connecting such adjacent marked points. So, we are going to look at the path, and all these points will be safe. So, that is because of this guarantee. So, safe SPAV and SPANT. So, we connect the adjacent points, form the path, but all this is we are not going to do it in the algorithm. We are going to compute the predicates directly, but this is the conceptual understanding. The insertion points are just before last computation in starting points of these paths, and then insertion edges are those that enter the junction nodes on these paths. So, it is as simple as that, and replacements are always for the last and first computations in the starting and ending points of these paths. So, let us demonstrate what we are doing. So, we say that a plus b is safe partially redundant in 4 in this case. Okay. So, this is the path from the first computation of a plus b to this particular expression a plus b. So, all these points are safe. Okay. We have this is the path that we are talking about, and this is the first point on the path and this is the last point on the path. In this we identify the last computation in this basic block. So, that happens to be this a plus b, and this of course is the first computation in the last basic block. So, because all these points are safe, we can replace this computation by x equal to h after we introduce h equal to a plus b, the rest remains the same. We also break this arc. This is the arc that enters this junction, this is at the junction. So, this it is entering this path. So, we have to break if there were this particular arc and introduce h equal to a plus b. So, now this a plus b will be replaced by h because h has the value of a plus b. So, this is precisely what we are talking about, replacements for last and first computations in the starting and ending points of these basic blocks. So, let us look at the details of the algorithm a little more. There are now we define what is availability, anticipability, etc., in the form of data flow equations. So, before that some local basic block properties have to be understood. So, for example, what is transparency of an expression in a basic block? So, this is a predicate, it is true for an expression in a node I if its operands are not modified by the execution of statements in node I. So, here is a picture, no assignments to A and B. Okay. So, A plus B is supposed to be the expression under consideration, no assignments to A and B. So, the expression value cannot be modified in any way. What is locally available or locally computed expression comp I, that is a property. True if there is at least one computation of the expression in I and no modification of the operands takes place during and after the computation. So, this is the situation x equal to A plus B, and then there are no assignments to A and B after this, and x cannot be A or B, otherwise x is being modified by the assignment itself. So, this is computed, transparency to an expression locally computed. So, after this computation A plus B is available at this point at the output of the basic block. What is locally anticipable property ant log I for a basic block I? It is true if there is at least one computation of the expression in I and no modification of the operands takes place before the first computation of the expression. So, there are no assignments to A and B here. In this case, that is not important. In the case of comp, there could have been assignments to A and B before x equal to A plus B. For transparency, none at all. But here there are no assignments to A and B, but and then you have x equal to A plus B. So, that means at this point this is anticipable, there are no modifications to A and B. So, this expression A plus B is anticipable. I can say okay, anticipability is true, that is why this is a locally anticipable property. Then we have the data flow equations. Availability. So, AV in and AV out at the input and output of the basic blocks. So, AV in is false if it is the start block. So, this is as before, for the start block availability of no expression is really true, no expressions are available at the entry block, okay, input of the entry block. And then the AV in at any other point, okay, any other input point of a basic block, you take the AV outs of the predecessors and do a AND operation. So, this is similar to the intersection operation in the available expression analysis problem. Here there is a slight modification, we are computing the properties of a single expression with respect to many basic blocks, whereas in the other case we were looking at the input and output points of basic blocks and computing how many expressions are available, etc., etc. So, availability of the predecessors is seen here. So, why is it that we are looking at an an AND operation on the predecessors? Well, availability says it must be available along all paths, that is why the AND operation is necessary here. What about the availability at the output point of a basic block? That is very easy. So, we can it is either computed in the basic block or it is available from the top and not modified. So, that is easy to see here. So, it is computed in the basic block and then of course, comp is true implies there are no modifications here. So, at this point the A plus B is available, or if it is available from the top, okay, and not modified at all, then also A plus B will be available here. So, these are the two situations that this handles. What about anticipability? For a basic block I, it is false if it is the end block. This is very similar to that very busy expressions. So, the end block. Otherwise, you look at the successors of the basic block and take the AND operation of the AND in values. So, why are we taking AND operation of the AND in values, we are looking at the successors. So, there may be many successors like that, and then all these successors actually must have anticipability true, otherwise anticipability will not be true at the output point of I. All paths, along all paths there must be anticipability, that is why you want the AND operation. What about AND in I? It is locally anticipable. So, that means here A plus B is computed and there are no assignments to A and B. So, locally anticipable at this point, or anticipable at the output point of I and not modified in the basic block. So, anticipable at this point and not modified makes it anticipable at this point also. So, that is what we mean. Then safety is either available or anticipable, both for input and output of the basic block. Now, we have a safe partial availability SPAV in I. So, this is false if I equal to S, of course, starting point as before in the case of AV in, or if the input point of I is not safe. So, because we also have safety as another parameter, I equal to S or safe in not of safe in I. In both cases SPAV in will be false. And the other part for other nodes, it is the OR operation sigma of the predecessors of the block I. Okay. So, take all the predecessors j of the block I, take the OR operation on the SPAV out values and that gives you SPAV in. So, why are we looking at the in the previous case here for AV in we looked at the predecessors, but we looked at the AND operation, whereas here we are looking at the OR operation. The reason is we want partial availability, that means any one of the paths will do, that is why this is OR operation. SPAV out is false if the output point of the basic block I is not safe, otherwise it is either computed or available from the top and transparent. This is as before. The safe partial anticipability at the output point of I is similar. It is false if I is either the end block or the output point is not safe. In other cases, again you take the union rather the OR operation of spant in j, where j are the successors. In the previous case we took successors, but we took AND operation. In this case again we take OR operation because we are looking at partial anticipability. Any one of the paths will do, that is why OR operation. And spant in is simple, false if the input point is not safe, otherwise locally anticipable or anticipable at the output point and not modified. So, this is as in this case. Okay. So, not much difference between these two. So, what is safe partial redundancy? So, there are again 2 points that we need to keep track of. One is the first at the entry of I and the last. Okay. First and last computations need to be considered specially. For the first computation in the basic block I at the entry of I, safe partially redundant I f, that is because it is the first computation we are looking at it as I f, is locally anticipable and safe partially available at the input point. So, this is safe partial redundancy, and last I when it is distinct from first I cannot be safe partially redundant, because the computations of the expression between these makes ANT-lock I false. So, you see we have the first and last computation here a little few here. So, we are really looking at first and last being very different. So, if they are the same, there is no problem at all. If they are different, that means after the first computation there have been modifications of the operands. Therefore, this computation needs to be present, this is not at all redundant, whereas this can be redundant because there could be something available from the top. Okay. So, if first and last do not coincide, that means there are modifications of A and B in between, and therefore, this last computation actually has to be cannot be seen as redundant computation of and replaced with some variable which stores A plus B here. We have to do a fresh computation of this again. So, that is what this really is saying. So, cannot be safe partially redundant because the computations of the expression between these makes ant log I false. Okay. Now, what is total redundancy? Total redundancy means locally anticipable and available from the top. Okay. So, that is very easy to understand, and then for the last I computation it is computed in the basic block and available just before that particular point P where the last computation is involved. So, total redundancy allows us to do common sub expression elimination, and that is precisely what happens. Every safe partial redundant computation is converted to a totally redundant computation, and then CSE happens to get applied there. Isolatedness is not a very important property for us today because it is only needed for proofs, but we will just look at it and understand. A computation is isolated if it is neither safe partially available nor safe partially anticipable at that point. So, this is not needed for us. So, we will skip the description of this. So, let us understand the various predicates. We have seen so far the various data flow values, availability, anticipability, safe partial availability, safe partial anticipability, and then safe partially redundant computation, etc. Now, the main task is to compute the predicates which tell you whether the computation has to be h equal to A plus B has to be inserted. So, let me give you an example. So, here is z equal to A plus B. So, if we replace this, then we would be actually z equal to A plus B would be replaced by h1 equal to A plus B and then z equal to h1. So, we call this as insertion of a new computation in the and this as a replacement. Okay. So, for example, x equal to A plus B in 1B has been replaced by x equal to h1. So, again this computation is inserted by breaking the edge. So, this is an insertion on the edge h equal to A plus B, h1 equal to A plus B, and again this is also a computation inserted on the edge. So, by breaking it, so it is h1 equal to A plus B, whereas this m equal to A plus B is only a replacement, and then A B are modified and n equal to A plus B recomputes A plus B. So, here observe that there is another variable h2 because there is a new computation. This cannot be taken as the same taken to be the same as m equal to A plus B. So, the value of A plus B and here are different. So, we have to do a recomputation of A plus B and that is done in a different variable h2. So, h2 equal to A plus B is an insertion and n equal to h2 is a replacement. This y equal to A plus B is replaced by y equal to h2. So, this is what we mean. So, there is an insert I predicate which says should I insert h equal to A plus B in this block in place of the just before the last computation in basic block I. So, it is always say remember we are going to do an insertion for the last computation and we are going to do only a replacement for the first computation. That is very clear in this example. So, here first and last computations are different. So, for this computation we have done a replacement and for this computation we are doing an insertion. And in this case first and last computations are identical, it is the same. So, we are doing both insertion and replacement. In this case also first and last computations are identical, but we do not need an insertion for, because the insert predicate will be false, but the replacement is being done. So, here is the insert predicate, insert I equal to comp I dot, that is AND operation, span out I, safe partially anticipable out I, and then AND with an OR operation, trans pi, not of trans pi plus not of spav in I, safe partially available in. So, this is not understandable straight away. Let us look at an explanation to understand this. So, comp I says expression should be computed in the basic block I. Of course, it should not, A and B should not be modified later. Then span out I, it says expression should be useful later. So, there is a computation of that expression later on. Safety is always woven through the entire predicate. So, everything is safe etc. So, with leaving out that safety, expression should be useful later is what anticipability is all about. Then this AND operation and then this predicate with OR, not of trans pi says operand should be modified in I, and not of spav in I says or expression should not be available from the top or above. So, let us see why this makes sense. So, expression should be computed in I. Obviously, if we are not computing something, there is no way you can insert and replace anything there. Okay. So, that is why computation is necessary. If you have x equal to a plus b, then I can insert a computation h equal to a plus b. If there is no computation of a plus b in that block, there is nothing to insert. Expression should be useful later. So, if this happens to be the last expression and there is no use after that expression later on, then there is no point in inserting h equal to a plus b and replacing x equal to a plus b by x equal to h. So, that is why anticipability later on is very important for us. Then this says operand should be modified in I or operand expression should not be available from the top. So, if the operands are not modified in I, then and of course, it is also available from the top, whatever is available from the top will just pass through. There is no need to actually compute that a plus b again. So, insertion need not be carried out, but if the operands are modified in the basic block, then there is a need to recompute that expression, and that is why this not of trans pi is makes sense. If the expression is not available from the top either, okay, then also we need to compute that expression. You can't simply take a value which already exists, there is not anything. So, this is the insert I is true only for the first node on the path and those intermediate nodes where the operands of the expression are modified and the expression is recomputed. So, that is taken care of by this part, the first node is taken care of by these things, okay, approximately, not exactly. So, let us look at an example. So, here is the node 1a, you have z equal to a plus b. So, as I already told you, here is a plus b and then the modification. So, this part is a second computation of a plus b. So, let us just look at this part first. So, this is the computation of the beginning and this is the usage and here is another usage in between. So, all these points are safe, safety is very easily computed. So, available here, this is anticipable here, available here and anticipable here. So, for different reasons all these points are safe. So, for this first point, the first and last computations coincide. So, insert I is true, right, and then the replace is also true. For this point, this is an intermediate computation. Now, we get this value from here. So, there is no need to compute this value again, provided we break this edge. Okay. So, that is why for this particular, assuming that we break this edge, this 1b insert is false and replacement happens to be true. So, we are only going to do a replacement. If we insert something here, it becomes fully available. And then we have this a plus b, this is the first computation in this block, right. So, for this insert 3 it is true, and replace is also true. Okay. So, but the insert part is for this last computation and not for the first computation. For the first computation, it is only the replacement that we look at, the 3f, okay, that is true. So, we are not going to do any insertion for the first computations. We always do the insertions for the last computation. Observe that here for the last computation. Okay. So, this will be replaced by m equal to h. So, that can be seen here. H1 equal to a plus b, z equal to h1. So, insertion and then replacement. Here we break this also, and then m equal to h1. So, why is this necessary to be broken? Because otherwise availability will be false along this part. So, let us look at the insertion on an edge. So, this is true if a computation should be inserted by splitting the edge I j. So, this is the one I was talking about some time ago. These are the edges which come into this path, okay, the safe path, and those are the ones we need to be broken. So, this edge is coming into this safe path, this edge is coming into this safe path. So, both these need to be broken. So, when is insert I j true? It is true if a computation should be inserted by splitting the edge I j, and insert I j is not of spav out I dot spav in j dot spant in j. So, let us understand what this is. So, if there is an edge, let us look at this example again. So, let us say we take this edge. Okay. We are going to do this computation for all edges and find out that it is not necessary to break this or this and so on and so forth. Only for these two we need to break them. So, this is I and this is j. Okay. This is I, this is j. So, it says insert I j not of spav out I. So, in other words, here it should not be safe partially available from the top. Okay. If it is already available from the top, there is a need to insert something here that can be used. So, safe partial availability is false at this point. Spav in j. So, this j point, the computation must be partially available from another path. Along this path it is not available, but from along another path it should be available. If it is not available along this path also, where is the point? There is nothing to be done at all. It is partially available, so we need to break this and make it fully available. Then it says spant in j. So, at this point the computation must be done later on, it should be useful later on, expression should be used later, it is recomputed later. Again, if there is no recomputation, why should we insert anything here? Okay. So, we for example, this is being computed, it is recomputed, this is one computation, this is another computation. So, along this path it is partially available, along this path a plus b is not partially available at all. Okay. So, we need to break this edge and then insert h equal to a plus b. The same is true along this part this edge as well. Here it is not safe partially available, along this path it is safe partially available, and at this point it is safe partially anticipable. So, we break this edge. So, that is what these three really mean. So, when is a replacement to be done? So, replacement of first and replacement of last, IF and IL. So, it is true if the first respectively last computation should be replaced. So, replace IF is ant lock I, spav in I plus trans pi dot spant out I. So, let us see what this is. So, when do you replace the first computation? Locally computed, that is the first computation itself, that is obviously true. Then spav in I, so available from the top, that is why we want to replace it by x equal to h. Otherwise, it is useful later on, okay, and of course, not modified. So, either this or that, one of these two must obviously be true. So, locally computed, make sure that we have the computation locally available, and then partial availability from the top or usefulness later on, one of these must be satisfied. Then we can actually replace the first computation by x equal to h. The last computation can be replaced provided it is computed in the block, okay, and then it is very similar, useful later on or available from the top and not modified. So, even though predicates look a bit difficult, it is very easy to look at the diagram and then see what is happening. So, here both the replacement is and the insertions are true. Here only replacement is true and only replacement is true. Here both insertion and replacement, and here only replacement. Okay. So, that is how these predicates really give you the value. So, for example, why should we replace this? It is available from the top. What about this? It is going to be used later on, and we would have inserted something just now. So, that is why this needs to be replaced. What about this? Again available from the top, we are going to break this and make it available. So, that is how these replacements happen. Now, let us take a slightly bigger example and see how this works. So, this has many loops and many paths and so on and so forth, and a plus b is again the expression. So, let us look at each of these properties one by one. So, these are local properties antlock, comp and trans p. So, antlock locally anticipable is true at at 2, 4, 7, 8, 9. So, why is it true here too? So, a plus b is here. So, at this point it is true. Then what about 4? And at this point a plus b is computed here. What about 7? Same thing, this is 7. So, a plus b is computed here. What about 8? Again a plus b is computed right here. So, it is true here. And what about 9? Again a plus b is computed here. So, comp is true at 2, 4, 7 and 9. So, in 2 because a plus b is here and then not modified later on. 4 a plus b is here not modified. Then 7 a plus b is here not modified, and 9 a plus b is here and not modified. Here it is not true because a plus b is here, but a is modified. Okay. Similarly, trans p, these are all empty blocks. So, nothing much happens, no modification here, but there is modification here, there is no modification. So, except for 8 and 2, all others are transparent. AV in is 5 because its expression a plus b is not available at the entry point of any basic block. Here it is not available, easy to see. Here it is not available because there is nothing here. Here it is not available because there is nothing here. And again this point, all this there is partial availability, but there is no availability at the entry point. AV out is true for 2, 4, 7, 9. So, AV out is true here because available because of the low computation, here also, and then 4 at this point also available. Anticipability is true at the input points of 2, 4, 5, 6, 7, 8, 9. So, why is it true here? Because a plus b is computed right here. So, let us take 7, again true because a plus b is computed right here, and 9 also the same thing. Safety is true for 2, 4, 5, 6, 7, 8, 9 because safety says either available or anticipable. So, in most cases local anticipability is true. So, write 2 available anticipability true even though availability is not true. So, in for the output points 7 for example, availability is true even though anticipability is also true, and at this point 9 the availability part is not true, okay, only partially available, but anticipability becomes true. So, safe partial availability is similar. This is a tricky one, others are very easy. 4, 5 and 8 SPAV in is true. So, let us take the input point of 4. So, why is safe partial availability true at the input point of 4? It is not the path alone that matters. If you take only the path partial availability, we can always trace this path like this, and then it is an availability, path of availability. But when you look at the safe partial availability, you must make sure that from the point of computation to this point all the intermediate points are safe. So, that means if we consider this as the computation which is available partially at this point, we have to make sure that this point, output of 3, input of 5, output of 5 are all safe. But unfortunately, 3 input and output are not safe, neither available nor anticipable. So, you can go out straight away. But partial availability, safe partial availability says from the point of computation to the point under consideration. So, we are going to take this as the point of computation, that is the output of 4, go through this part 5, come out and then go to input of 4. So, this is the path of availability that will be considered to make sure that safe SPAV in of 4 is true. So, it is computed here and then brought back. So, that is say a partial availability again. So, this is true for this path also, I can always take this path like this, right, and then like this compute and then go out and then come again. So, that is the path, and since we are going to take from the computation point to the point under consideration, we need to consider only this path. So, output of 4, input of 5, output of 5, all these are safe. Okay. So, safe in, safe out has 5 and 4, no problem. So, SPAV out is very straightforward. Let us take 5. SPAV out of 5 is true because I get something here and then this is transparent, and of course, safety is true for all these blocks. Spant in is let us spant in is simple because there are too many blocks here. Let us take spant out of say 6. So, we are considering block 6, right. So, then output point of block 6. So, it does not matter how we want to go out, this is the only path available to us, a plus b is computed here. So, anticipability becomes true. So, that is so far as safety etcetera etcetera. Now, what about insertion and replacement? So, in fact, this that is in the next slide, this cannot be neither replaced nor used as a redundant computation. Okay. So, we have to break this edge and insert a computation here. This computation gets a replacement, this computation gets both a replacement and an insertion. Here this gets a replacement, but there is nothing we can do for this computation either. Why? See, the point is if you look at this edge, okay, this is a critical edge. So, at this point we do not have safe partial availability, and at this point we have safe partial availability, right. So, this is the insert ij is here, safe partial availability of this point is false, this point is true, and spant in j is also true at this point. So, this is a critical edge when we need to break it. But the immediate question will be, okay, breaking this is fine. If I break this edge here, okay, then I am inserting an a plus b here, and that solves all my problems. It makes it available for everything that goes out. Okay. So, I can replace this, I can replace this, I can replace this, I can replace this also. and I cannot replace this because A is modified of course at this point. So, I can replace all these by inserting a computation right here. So, why are not we doing it? Why should we not split the edge 1 3 and replace the computation h equal to a plus b? Why only on the edge 3 5? The answer is it is not safe. The path 1 3 10 had no computation of a plus b before transformation, and by placing a computation on the edge 1 3 we are introducing 1. So, 1 3 and 10 had no computation, whereas if we introduce 1 here, this gets one computation and this becomes unsafe. Whereas, if we introduce 1 here, this already had a computation. Okay. So, for example, if you had taken this path, it already had this computation. So, there was no problem. That is the reason why we insert the computation here and not at this point. And I can't replace this a plus b by a previous computation because a is being modified here. So, that is why it fails for this point as well. So, that is how we do the computations, and this is the insight for why certain computations are replaced, why are certain edges broken, etc., etc. So, the final solution is something we already said. So, let us not waste time there. There are certain correctness results that we need to be aware of. So, couple of lemmas and theorems. We are not going to prove them, but let us state them. Lemma 1 says all insertions of computations corresponding to the transformation are done at safe points. So, by definition of that insert and insert ij etc., we always use spant in, spant out etc., and spav in, spav out. So, that means the transformations are automatically carried out at safe points. This is the intuitive explanation. Lemma 2 says all candidate computations which are safe partially redundant become totally redundant after insertions corresponding to the transformation. So, something may become partially redundant, but it may not be safe partially redundant. So, in such a case we will not be replacing it, only when the safe partially redundant computation is available we replace it. Lemma 3 says only, so we have woven this safety completely into the insert and replace predicates, and that is how this becomes true only for safe partially redundant computations. Only those candidate computations which would be redundant after insertions corresponding to the transformation are replaced. So, this is again true because otherwise we would have replaced this also, So, that is not true, right. So, they should become completely redundant. Here this does not become redundant. A equal to C makes sure that we have to recompute this all over again, and this also does not become redundant because A equal to C is modifying A. After the transformation, no path contains more computations of an expression than it contained before. So, this is something we already assured. So, we did not want to insert anything by breaking this edge. So, otherwise this would have had an extra computation. Okay. And of course, not only that, if when we inserted something here, we took away something at this point, right. So, we had a computation here along this path. By breaking this edge, we introduced a computation here, but we took away that computation. This computation remained, it is only a question of making it h equal to a plus b from x equal to a plus b. So, the theorem says the algorithm performs partial redundancy elimination correctly, it is based on these lemmas. Then the fifth lemma says a candidate computation is not replaced by a the transformation if and only if it is an isolated computation. This is what I was saying. So, unnecessary computations are not really replaced. So, that is something like in this case, for example, this computation is not replaced, this computation is not replaced, etc. Theorem 2 says the transformation is computationally optimal. This is an important result, that is there does not exist any other correct transformation with less number of computations of an expression on any path. So, we have introduced the minimum number of computations necessary. We have not introduced even one extra computation, everything is optimal. Okay. And finally, the theorem 3 says the transformation is lifetime optimal, that is the transformation keeps the live ranges of the newly introduced temporaries to the minimum. So, what this really says is we have introduced these temporaries h, h1, h2 etcetera at the points where its live range becomes the smallest. I could not have pushed this to this point, that is what, or this point without sacrificing either safety or any other property. So, that is why this property becomes important, the theorem becomes important, it is lifetime optimal. So, live ranges are kept to the minimum. So, this is an overview of the partial redundancy elimination algorithm with examples. We have not really proved any theorems, but I hope it has given you an insight into how the algorithm really works. So, thank you very much. This is the end of the lecture.